it will be very easy for me. Then I will switch a little bit, not change the topic. We will still talk about membranes, but this time from the computational point of view. So I will tell you a bit about modeling and simulation of membranes, actually. So please let me start with the acknowledgement, then be sure not to forget this at the end of the presentation. So a special thanks to my PhD students and postdocs who did the most part of the work, actually. SZYMCZYK, Rissa Renou and Helmi Hidil Mohamed. Thanks also to the colleagues from the lab and from abroad, especially Dr. Aziz Goufi for performing, writing most of the simulations I will show you today. Beatrice Balanek, my colleague in the lab, Emil Drazevic from Croatia, Patrice Malfren from Goujon from the Université of Clermont-Ferrand in France, Lydie Pogam, another collaborator in Rennes, and Professor Armand Saldera from Canada. A big thank to the CEFIPRA, of course, because it is thanks to the CEFIPRA that we are all here today. Especially through the funding of this networking project Swatchnear in Vimeyer. In Vimeyer, this is French, so in English it means a better life. Okay. Thanks also to the following institutions for funding our work. Okay, so this is the outline of the presentation. I will start with the molecular simulation of membranes, so microscopic modeling, and then I'll move on a much bigger scale. And we'll tell you about macroscopic modeling, what is named as continuum-based transform modeling. So as all of you know, water scarcity is now a global concern. We heard that before, of course. This could be a bit surprising at first sight because actually the amount of available water on Earth is huge. It is estimated to be about roughly 1.4 billion of cubic kilometers, so this is really a huge resource. Unfortunately, the big majority of this resource is actually seawater. It is estimated to be about 97% of the global resource. So it means that we only have 3% of the global resource as fresh water. And unfortunately, these 3% are mainly located in polar ices or are hardly accessible groundwater. So say that roughly 0.3% of the global resource is actually usable for human consumptions and for ecosystem. And that points out the necessity for water reuse and water desalination if we want to be able to increase water supply beyond what is available from the natural hydrological cycle. So within this context, membrane separation processes appear to be very attractive candidates because they are energy efficient, since no phase change is required to operate the separation. They are also relatively environmentally friendly in the sense that they need no additions or say a limited addition of chemicals to operate. They already found a lot of applications in various industrial fields, various industrial sectors, but we have to admit that there is clearly a main drawback or a main bottleneck, I should say. Nowadays, the main bottleneck is that transport mechanisms through the membranes are not yet fully understood. So we have to work on it. So within this context, why do we need modeling and simulations? Of course, to get a better understanding of how and why a process or a material works, but also modeling can be very useful to optimize a process while limiting all these costly, time-consuming experiments, trial and error experiments. So you can save a lot of time if you use a proper and appropriate model, for instance. If we focus more specifically on molecular simulations, then can be very helpful because they can be a very attractive tool to determine some physical quantities that can be very difficult to measure experimentally, and in some cases it can be impossible to measure these quantities. And finally, we should not forget that solutions often come from adapting materials at the molecular level. Okay, so let me start with molecular dynamic simulations. I guess not all of you are familiar with this molecular simulation technique, so I will just summarize or remind you the basic principles of the methods. It's not very complicated to understand. It is much more complicated to implement, but the principles are quite simple. If we focus on molecular dynamics, actually that is one class of molecular simulation methods. the aim of which is to determine the time evolution of the atomic positions and the velocities of a system of particles that interact with each other via a force field. In this context, the force field is a set of parameters, you can see here an example, that enables you to compute the potential energy of the system. Okay? Depending on the force field, you will have different expression, different set of parameters, but in all cases, you will be able to take into account both the intramolecular interactions and intermolecular interactions. Then, considering a given statistical ensemble, you will be able to determine the time evolution of both the positions and the velocities of the different particles. So this is a microscopic, this is information at the microscopic level. And then, thanks to statistical physics, you will be able to determine some macroscopic properties of the system. Okay? Well, this slide is just it is a very schematic representation of how a molecular dynamics simulation runs. Actually, everything starts with an initial configuration where both the atomic positions and the velocities of all the different atoms must be set in your simulation. Okay? Then, from these positions, the force field is used to compute the potential energy of the system at the initial time of the simulation. Taking the first derivative of the potential energy, you can get the force acting on a given particle at this time. And thanks to the second Newton's law, that is the equation of motion, you can determine the acceleration of this particular particle. Okay? Now, by using an appropriate algorithm, you will be able to integrate this equation of motion and then to determine the new position and the new velocities at time t plus delta t, where delta t represents the time step of the simulation. And of course, if you repeat this loop, if you repeat this procedure a given number of times, then you can get the trajectories of the different particles over the simulation time. Okay. The point is that in molecular dynamics simulations, the time step you use must be short enough. It must be small enough in order to get accurate trajectories. And typically in molecular dynamics simulations, the time step is roughly 1 femtosecond, 10 to the minus 15. So it means that if you want to simulate a single nanosecond, you have to repeat this procedure 1,000,000 times. Okay, and this is just for particle I. So you have to do it for all particles in the system. So of course you can understand that the limit of this kind of tools will be computing resources. Okay, this is very, very demanding in terms of computing resources. Now, what can we do with this kind of tools? I chose a couple of examples here. First, considering what I will call model nanopores, carbon nanotubes, nanoporous graphene, and so on. Very model materials, very interesting materials, let's say. For people coming from membrane science, this is very model systems. So in this first example, we consider a carbon nanotube and water filling this nanotube. So first, you can get very instructive information regarding the structure of the fluids that are confined inside the nanopores. For instance, in this picture on the left, you have the radial profile of the local density of water inside the nanopore. So in a bulk phase, this curve should be flat because the density is the same everywhere in the system. This is no longer the case inside the nanopore because of confinement effect. And if you look at, so the density, let me check. Yeah, the density is represented by the circle, the white circle. If you check the profile, you observe this series of peak, valley, another peak with a smaller amplitude, valley, and then you retrieve a bulk-like behavior. But what does it mean, these peaks and valley? It means that water actually water molecules organize themselves inside the nanopore because of confinement effect, and they adopt a structuration, a layering structuration. This is what you can see in this picture. You see that this is the wall of the nanotube, and this is the water inside. You have this first layer of water and another one in the second. Okay? So this is the first layer and the second layer of water. What happens if you remove the nanotubes? Then you can see here the structuration just vanishes and you retrieve a bulk-like organization. Okay? What was interesting here is that we also use molecular dynamics simulations to compute the dielectric permittivity of water inside the nanotube. And the results are shown by the black line here. And you can clearly see a very strong correlation between water structure, the circle, and water dielectric constant inside the nanopore. So this is this kind of information you can get. That would be very extremely difficult to measure this experimentally. Okay. Well, another example, still considering carbon nanotubes. In that case, we focused on diffusion inside the system. If I'm right, yes, in this example it was not water, but it doesn't matter. We investigate the behavior of ionic liquids inside this kind of systems. And we observed that for many systems based on carbon nanotubes, we can get a higher diffusion inside the nanotube than in the bulk phase, which was quite surprising. And that was especially true if you consider this particular carbon nanotubes 2020. The self-diffusion coefficient of ionic liquids was many times higher than in the bulk phase. The bulk is represented by the line here. Actually, the reason for this was we were able to explain that thanks to molecular simulations. If you look at this figure on the bottom left, then you have two curves representing the translational motion of the ionic liquid inside the nanotube and the azimuthal motion. Okay? And what you can see here is that both motions are strongly coupled, which means actually that inside the nanotube, the ionic liquids diffuse according to an helicoidal movement, or what we call a spiral motion. If it works, you can see that. Yeah. If the movie. Yeah. You can see the ionic liquids diffusing according to the spiral motion. And from time to time, you have this kind of jump, which accelerates actually the diffusion compared to the bulk phase. So that could be very interesting if you can manipulate this kind of movement. Suppose you can do that with water in order to increase the permeability through the system. Another example, this time we consider graphene, and we drill a hole, a nanopore, inside a graphene sheet in order to produce a graphene monolayer membrane. In that case, there are some studies that have been published in the literature showing that nanoporous graphene membranes would be able to transport water very fast. The permeability is increased by maybe 3 or 4 orders of magnitude if you compare with polymer membranes. So we try to see if we obtain this kind of result with the simulation. So it's true. If we compute the water molecules flowing through the nanoporous graphene as a function of the pressure difference applied to the system, we have, so graphene is shown by the triangle you have here. So this is much higher than what we can get in a polymer membrane. But what we did at this time is try to see if another kind of materials could also show the same performance. And we focused our attention on boron nitride. Boron nitride is also very similar to graphene because boron and nitrogen are isoelectric systems. Yeah, one is just before a carbon in the periodic table, and the other one is just after it. So boron nitride and graphene are isoelectric systems. So very similar. And then the question was, okay, maybe nanoporous boron nitride could be also efficient. And actually, what we observed is that if you consider monolayers of nanoporous boron nitride, the permeability, the water permeability, is even higher than what you get through graphene. So, well, this is just the start of the work, but the question is that boron nitride could maybe could be a future candidate for membrane materials if we think about water desalination. Well, as I said, these carbon nanotubes, graphene, boron nitrides are very interesting, fantastic materials. But the truth is that currently they are not used at the industrial scale to produce membranes. You don't use graphene membranes in water treatment industry nowadays. Everything is done, as Patrick said, with polymer membrane. And if we focus especially on water desalination, the dominant class of polymer membranes today are polyamide membranes. They are basically thin film composite systems made of, say, at least 3 different layers, a coarse porous and rather thick support that brings the mechanical strength of the membrane, an intermediate layer, usually it is polysulfone, and there's very thin and very dense skin layer that is polyamide, actually, and that rules the separation performance of your membrane. So typically this is the chemical formula of the the most dominant reverse osmosis membranes available on the market nowadays. So based on two aromatic monomers, diamine and trifunctional acid chloride, that leads to the formation of a very dense and a highly cross-linked polymer. So what we did in a lab, we developed a methodology to build an atomic model of such a polymer membrane. Well, I don't have time to go into details, but you can see that starting from the monomer, thanks to quantum calculations, we can determine the partial charges, the different partial charges of different atoms, build the linear, the polymer chains, pack the chains, cross-link the system, and then at the end we succeeded to generate this atomic model of a polyamide membrane, which has a cross-linking degree that is very close to what can be measured experimentally. So we think that it should be a fairly representative system of reality. The next step was to hydrate the membrane. So it should work, I think. So what we did here was we put two different walls, two walls on both sides of the simulation, and these walls were used as pistons. So we just press on the system to force water molecule to enter the membrane. Well, maybe it's not very clear here. You have the membrane and water molecule progressively entering inside the polymer. Okay. So if you count the number of water molecules entering inside your polymer membrane as a function of time, you can determine, after a given simulation time, of course, you can determine the equilibrium water uptake of the membrane. So, for instance, we got a rather high value, actually, 24%. 24%, this is weight percentage, 24% of water inside the membrane. This is very high because the system is actually very, very dense. The cavities of the free volume elements between the polymer chains are no more than, say, maybe around 5 angstroms. So this is extremely dense, and then it's going to be quite surprising that this membrane can take 24% of water in weight percentage. But actually, if you compare with experiments, this is the blue line, okay, you see that there is a very, very good agreement between the simulation and